Welcome everybody to our community conversations with experts, or actually we call it now Ask an Expert. My name is Esther Hars and I'm the mother of a patient. She's actually 10 now, and I'm also the president and CEO of the SDS Alliance and your host today. Um, my co-moderator is usually Joyce, and she may or may not be able to join today. She has some other work obligations, but we will see. Joyce is a high school student with SDS and a rising star in patient advocacy. So I hope she will join us too. Some housekeeping items. This session is being recorded and will be posted online. Your privacy as patients is very important to us, so we will remove your personal identifiable information such as your name and your video unless you expressly tell us otherwise. We are using the Google Meet platform, and the controls are on the bottom of the screen. There is a microphone and camera button, raise your hand button. Um, Occasionally, the sound and video is not available to some people. Maybe it depends on the device, but you should be able to enter questions and comments in the chat function, which is the little speech bubble looking icon on the bottom right. Questions and conversations of public interest are encouraged, but please don't offer medical advice and don't ask for direct medical advice relevant to your particular situation. Uh, Please also adhere to our community guidelines. They're posted in the footer of our website, sdsalliance.org. And feedback on contents, logistics, anything is also very welcome, both at the end of the meeting and offline as well. So without further ado, it's my pleasure to introduce Dr. Lisa McReynolds as our expert today. She's a pediatric hematologist oncologist and inherited bone marrow failure expert out of Bethesda, Maryland. And our topic today is pretty broad to encourage a conversation. Basically, what are clones, germline, and some somatic mutations, and why do they matter for SDS? It's my pleasure to hand over the microphone to Lisa.
Great. Thank you so much. And thank you to the SDS Alliance for having me here. I do want to say that, whatever I say today is my own personal opinion and not reflective of my employers. And I also, like Esther mentioned, don't want to give any direct medical advice. So please reach out to your providers for any specific advice that you may need. All right. Hopefully that looks okay. And now I can't see you guys. So don't raise your hand if any, just interrupt me. If you have any questions, this is very much a conversation. So just reach out because I can't see people anymore. So we had talked about two topics that I wanted to cover today. The first is the genetic testing and the importance of genetic testing, and then talk about clones, somatic versus germline. And I'm only going to talk for like 10, 15 minutes at most. And then we have either, the rest of the hour to answer questions. So genetic testing in bone marrow failure syndromes is quite common. Bone marrow failure can be both what we say acquired. Some people used to call this idiopathic, which just means we don't have a good reason for it, but now we really like to use the term acquired. And then there are inherited forms of bone marrow failure, which are, genetically driven. And these can be really difficult to tease apart which is which, but it's really important to figure out which is which because the treatments are completely different between the acquired and the genetic disorders. And overall, a significant number of patients with bone marrow failure do have an underlying genetic cause, and getting at that is really important. So one of the papers that we had recently written, Esther had asked me to talk about. So we took a large group of patients who were actually identified to have supposed acquired bone marrow failure and looked in them and saw how many people had what we termed unrecognized inherited marrow failure. So these people had all their workup and be seen by many experts and had bone marrow transplant, but actually had a missed inherited bone marrow failure diagnosis. And that turned out to be about 6.5% of the group of almost 700 patients that we had looked at. And if we looked at the different types of disorders that we could see, so in panel B on the left-hand side, so these were patients who had their unrecognized inherited marrow failure, and about 12% of these patients had ribosome biology disorders like SDS. This also includes DBA in this group here. And then the other things were DNA damage response disorders. These include mostly Fanconi anemia patients, and then telomere biology disorders, that's dyskeratosis congenita. And then the group that we termed the hematopoiesis disorders, this is like the more newly described GATA2 deficiency and RUNX1, which is also called familial platelet disorder. But you can see a decent percent of these patients are ribosome biology disorders, including Shwachman. And some of these disorders are recessive, meaning, right, you need 2 pathogenic variants to acquire the disorder. And again, if you're looking at how many carriers were in the group, about 12% of them had a ribosome biology disorder. And really, these have little impact, but they're important to identify for donor identification and for family testing. And a couple of months ago, I had given a talk about the importance of genetic testing to the Aplastic Anemia and Myelodysplastic Syndrome International Foundation. And one of the things that they were really trying to talk about is like, how can we advocate for our patients to get genetic testing, and why does it matter so much? And so this is a really busy graph, but if you focus just in on the blue line, this shows you the rate of a germline finding amongst patients with either bone marrow failure or myelodysplastic syndrome. And you can see a great peak, right, in the pediatric and young adult age range, and then there's a bit of a tail as you go forward. And what this really is talking about is that regardless of age, the rate of a germline genetic testing outcome is greater than 5%. And why do we care about 5%? So 5% is the rate that they use, the national societies use. If your rate of finding a genetic reason is more than 5%, then we should test the germline. And no matter what age you are, your risk of having a germline finding with bone marrow failure is more than 5%, and in childhood, way more than 5%. And so it really is important for all patients with bone marrow failure to get genetic testing. And as we all know, this can be a big hurdle for many patients. So why do we care? So the family history and the physical exam aren't always great predictors of a genetic cause. For many years, everybody thought that we could identify patients just on physical findings as having an inherited disorder. And what we really show now is that many patients don't have any physical findings on exam. And genetic testing information is really important for treatment decisions going forward. And then for what we call cascade testing, meaning family member testing for children, siblings, and other particularly donor family members, it really makes a difference. And the speed and cost of genetic testing has come down drastically in recent years and really made it much easier. 40 years ago, it was, we would test one gene at a time. It was very expensive, and would go from one gene to the next to the next. And now, we're able to do large panels of genes, or even what's called whole exome sequencing, where we sequence the entire coding regions, and even whole genome sequencing. And this has really gotten a lot cheaper, and it's really much easier these days to get it. And honestly, genetic testing is often much cheaper than other testing that patients get, but it is kind of still very much thought of as a very expensive test, even though it's often not that expensive anymore. The type of genetic testing, meaning, should you have a single gene test, should you have a panel, should you have an exome, is really best determined by your healthcare provider. And I can tell you, I was recently at the curating the clinical genome convention just a couple weeks ago, and this is really a hot topic now, and the thoughts on what's the best testing to get is really evolving, and I think that has to do with improving technologies and decreasing costs. But as many of you know, insurance coverage remains a big hurdle, and this is a problem. And I would say we spend a lot of time advocating for patients to get genetic testing, but patients who are uninsured or underinsured often get denied genetic testing, and that's really a disparity that's a problem across the community that we need to really work on. So that's what I wanted to say about genetic testing. And then Esther had asked me to talk a little bit about the difference between somatic and germline variants. And when I say variants, for a long time we use the word mutation, and now we really like to talk about these as variants because they really are just variants that people have that are from slightly different from other people. And so we're just going to talk a little bit about explaining those two different things. So a germline variant, right, is something that you're born with, and you have it when you grow up, and you have it in every single cell of your body. Typically, these are inherited from your biological parents, although there are a decent number of patients with bone marrow failure syndromes who have what are called de novo variants. So this means this occurred really early on in development, and therefore is in every single cell, but isn't actually inherited from your biological parents. But importantly, it's present in all the cells in your body. And this is to contrast that with mosaic or somatic variants. So people like to use the word somatic. Mosaic sometimes, but I very much prefer to use the word somatic because it saves a lot of confusion. So these variants, right, you're not born with and are only present after birth, and they only present in some cells. And this occurs mainly in tissues that have a high turnover rate, particularly things like your blood cells and say your epithelial lining of your intestine. And so they really only occur in some of these variants occur in some of the tissues. So this is just a cartoon, and I'm not the best drawer, so bear with me. So in this one, right, so if a stem cell has, a germline variant, and then its offspring have all the germline variants, and in the case of Shwachman-Diamond syndrome caused by SDBS variants, you have all cells have two germline variants. And when you had genetic testing using next generation sequencing technology, your reports will often have something called a VAF, or variant allele frequency. And this is how we represent how many of those molecules that got sequenced have either the reference allele or the variant allele. And if you have two copies of the same variant, what we call homozygous at a position, it'll be 100%. If you have two different variants in the same gene, the VAF will be 50% for each of them. And this is really to contrast to somatic variants, right? So if we have somatic variants, then one cell acquires an additional somatic variant, that's the little star, and the other cells don't have that somatic variant. So out of these 10 cells, right, 2 of them have the somatic variant, and the variant allele frequency will be 20%. And some of the variants, somatic variants identified on different technologies, and they aren't reported as a VAF. This is usually typical for large chromosomal changes, and they don't give you a VAF for that. So this is really only for the small variants that are only 1 or 2 nucleotides. So what happens to these cells with somatic variants? Sometimes they just stick around and you have them for a long time, and either they don't do anything or they go away. But sometimes they can, you can acquire additional variants. And we say that this can be either two things, either adaptive or maladaptive, meaning the additional variant can help the cell make it do better, function better, or it can be maladaptive, meaning it can give it properties that you don't want that cell to have, meaning saying it'll multiply too fast, or it will act in a way that causes, a detriment to the host. And some of this has been extremely well worked out in Shwachman-Diamond syndrome. There's a paper by Alyssa Kennedy in 2021, and she looked at a group of patients with Shwachman-Diamond syndrome and looked at their bone marrow and looked at what kinds of somatic events that they had gotten. And so they represent this, they call this fitness, meaning how well the cells are functioning. So in the gray bar is normal, and then the first column, right, your cells are fit, right? If you have Shwachman-Diamond syndrome, you have ribosomal stress, and your bone marrow cells don't work as well. And then some of these cells can acquire a somatic variant. In particular, what's common is something called a variant in a gene called EIF6. And this improves your fitness a little bit. So it gets better, right? But it doesn't make it totally normal. And then sometimes you can acquire another somatic variant in a gene called TP53. And that makes it a little bit worse, right? We are sort of maladaptive. And sometimes then you can get a second TP53 somatic variant, and that makes the fitness, what you can see here, how they've depicted it, it gets better, which is not a good thing, right? Because the cells are surviving when they should be dying off. So that's just an example. There are many other examples of somatic variants, and not all patients get these two variants, but this is the model that they had worked out in this paper. So why do we follow somatic variants in patients with inherited bone marrow failure syndromes? So some of them can really help us guide treatment decisions. And some of them can help project what might happen to a patient over time. But for the most part, a lot of them we don't know yet. And we really hope that in the future we'll be able to refine these tools to really understand when we need to intervene and when we don't need to intervene, and which ones are predictive and which ones aren't predictive. But this is where the science is going, and things that we really need to work on going forward. So those are just the points I wanted to make on these two topics. And I'm happy to take any questions or see what this brings up for people in terms of thoughts going forward.
Mm-hmm. Yeah, thank you. Thank you so much. I think this gives us a lot to inspire some questions, but maybe to melt the ice. Let's see if the kids are ready to ask their questions first. Anna, Banana, or Penguin, are you guys ready to ask questions? Let's see.
Penguin isn't asking questions. She doesn't feel like it.
Okay, only you. All right.
It's just
Yeah.
me.
So yes. All right. So ask your first question then.
Oh, wait. Do you want to? Okay. What does your day-to-day work look like? Is it in a lab, at a desk, or do you see patients?
That's a great question. So I do a little bit of all three. So my job is officially called a physician scientist. So that means I do see patients and I do science experiments, and I sit at a desk too sometimes. So really, it depends on the day of the week. And I really enjoy getting to do all three things. I get a lot of joy about seeing patients, and the science experiments keep me going and inspired. And then, we have to do the hard work of writing what we're doing and presenting. And then, of course, there's always, the unfun part of the just logistical day-to-day paperwork stuff that has to get done at a desk too. So I do a little bit of all of those things.
Why did you decide to become a scientist or a doctor that you learned?
That's a great question. So when I was a little kid, very young, I had always wanted to be a doctor. And then when I was about 12 years old, actually I was in 7th grade, which is the age my son is right now, I got really inspired by science and got really interested in science. But I didn't grow up with any doctors or scientists in my family, so really didn't know anything about it. And then I got this wonderful opportunity in high school to work in a lab. At first, I just washed dishes and cleaned glassware and did very boring things. And then I was lucky enough to have somebody take me under their wing and teach me about, what it was like to be a scientist and what I would have to do to be a scientist. And I really loved that. But I had always wanted to be a doctor, and I felt very conflicted. And then I went to college, and I still didn't know what I wanted to do. And then somebody said, well, why don't you do both? And I said, well, what's that? And they said, well, you could be a physician scientist. And I thought, well, that sounds up my alley. And so that's what I did.
Yeah, very cool. Like I wish I had the foresight. I was more interested in science. But now that I work so much with patients too, I'm starting to think that maybe that mixed path would have worked better for me too. But here we are.
You never
That's
know.
not reading.
Next questions, kids?
What is your favorite part of the day?
I think my favorite part of my workday is actually I get to teach a lot of, we have a lot of trainees who come where I work between college and their next step in their career. And I really enjoy teaching them how to become scientists and showing them the ropes. I find that really satisfying. And I've had two of my students go on to be genetic counselors, and to see them do well and thrive is when I feel the most happy in my work. I also love taking care of patients, and I love to see when they do well as well. But I would say I see patients less than I see my students. So that's just my particular job.
Mm-hmm. Oh, that's an interesting, so this mentorship.
Mentorship, yeah, yes.
Mm-hmm.
And I was very lucky because, as I mentioned, I didn't grow up in a science family, and I really didn't. My parents didn't really know how to help me, and I had wonderful mentors, and that made a really big difference for me. So I try to be that person for someone else.
It's beautiful. Kids, do you have any more questions on your list?
Have you met any STS patients in person?
Oh, yes, I have. Not because of my work, we don't see a ton of patients, so I would say the numbers are very small. But yes, I have seen STS patients in person.
And then there's one more question from me. What do you like to do in your free time?
That's a good question. So like I mentioned, I have a 12-year-old son, and he's a big baseball player. So I love going to watch him play baseball. And I have a dog, and I love to take him on long walks. That's my me time. So yeah. If it would stop raining. It's been raining in Maryland like nonstop this spring. So.
Great. So thank you, kids, for breaking the ice. I'll have a question, but I hold mine for later. So we can go to the audience questions. And I see Jackie has raised her hand.
Do we ever see non-germline variants in the inherited bone marrow failure diseases? I mean, by the virtue of the name inherited.
Meaning de novo variants?
Right. Is there such a thing? And if so...
Yeah. So we certainly do see patients, particularly patients who have inherited one, and then they have a de novo variant, meaning, right, so it occurred either in the sperm or the egg or in the early zygote on the second allele. Tends to be the most common. It's less common in SCS than in some of the other inherited marrow failures, but it's definitely, that was the situation. So, yeah.
And was that likely because of some crossover event with the pseudogene, or really just completely random?
That's a really great question. I haven't done a survey of all the de novo patients, although that would be really interesting to look at. Certainly some of the patients who have very large deletions, they're large chromosomal deletions, and I don't think that that's necessarily related to the pseudogene. But we didn't look, so it's possible. Yeah.
Mm-hmm. And then the other thing that Jackie's question could be interpreted is could somebody acquire, say, an SBDS mutation as a somatic mutation, but somehow, I guess it wouldn't grow to really cause a problem, right? Because those cells are not that fit. But maybe something like a RUNX1 or some other genes that don't decrease fitness, they could potentially cause problems just as a somatic mutation.
We see patients who are truly mosaic, right? So in terms of So they had an early post-zygotic event, right? So then they have mutations only in a subset of cells. And we see this not infrequently in Fanconi anemia. So these patients do have, so the classic hallmark of Fanconi anemia, right, is chromosome breakage. So they still have a positive chromosome breakage test, but not in all their cells. And typically, right, so because of what you're bringing up, Esther, right, so the cells that don't have the mutations, right, are more fit, they survive, they do better, right? So their blood system tends to be, their hematopoiesis is mostly mosaic in the wild type direction, right, the non-variant direction. But some of their other cells may be, carry the pathogenic variants. I think we see less patients with somatic SCS variants compared to other inherited bone marrow failure syndromes, but it doesn't mean it doesn't occur. And I think these patients are often underdiagnosed because their symptoms may be more subtle, right? And and so much of it depends on how that mosaic pattern has sorted itself out.
Mm-hmm. Yeah, I've been thinking about mosaics in the context of, I think that phenomenon in Fanconi anemia actually worked in the favor of therapy development because it gives scientists and researchers some confidence that gene therapy, it's kind of like a natural gene therapy in some ways. But we don't see that too much in STS, except that some of the good mutations that they can acquire, right, the IEF6 mutations, not the P53 ones, but the other ones, if they persist, that it is almost also like a mosaic, right? And that kind of supports the idea that increasing the fitness of cells in a good way could be beneficial to patients in the long run.
For sure. And we see this in, right, so like in the setting of bone marrow transplant, right, patients become mixed, right? So we call that chimerism, right?
Yeah.
And so, in some diseases, when you have a bone marrow transplant, the donor cells are going to take over because they're just so much fitter, right? They're going to work so much better. They're going to crowd out the cells that don't work well. In contrast, say for a disorder like sickle cell disease, right, there's no advantage for those hematopoietic stem cells, right, to take over the bone marrow, right? So patients who get transplanted for that indication, sorry, that's my dog, right, they have a much harder time becoming fully 100% chimeric. Sorry, my neighbor's coming home, therefore he thinks he must bark. So yeah, so it depends, right, on the situation. And I think, in the example you bring up in Fanconi anemia, right, we know that those cells are going to do better and they're going to make up enough of the bone marrow. So, well, the genetic, the trials are still going on. We still haven't proven that it works. I think we have a little more confidence because we know about Fanconi patients do well when they are mosaic. It's not fixed, right? It only fixes the hematopoietic compartment, right? And so we have to be careful about thinking about it as a cure-all because it doesn't fix the other cells in your body, right?
Right. But I guess it gives some confidence that maybe for some types of gene therapy, we would not need to replace 100% of the stem cells, and there still could be a beneficial effect.
For sure. Mm-hmm. Yeah. Jackie, did you have a follow-up question?
Yeah, I actually did. So, and I had spoken to Blanche Alter about this at some point, and we know that in STS, if we had 100% involvement, it would be incompatible with life. So there is some functionality in some of the cells. How do we get to that point, and how can we promote functionality?
Yeah, that's a good question. I don't think I really have an answer to that question. I mean, I think there's clearly some SBDS protein function in each individual cell. And,
Yes.
could upregulating that in some way help, right? Could we compensate for the ribosome defect in such a way that it would be enough to make those cells function in the way they're supposed to? It's possible. I don't think we have an answer to that yet, but it's totally possible. And you have to always be really careful about like the setting, right? It's a little bit too much is a problem, right? And too little is a problem, and it's very much a rheostat, right? You know, it's your light dimmer. But I think it would be really interesting to see, and that's certainly something that people have tried in other disease settings. You know, I don't know what the status is in Shwachman. I haven't heard about anything, but that doesn't mean it doesn't exist.
Well, in a way, Dr. Warren's work on the small molecules, right? What he's looking for are small molecules that would decrease the binding affinity of IEF6 to the ribosome, where usually the SBDS protein would be in charge of removing the IF6, and he's looking to support that reaction with small molecules. So I guess that would go in the direction, Jackie, that you were hinting at.
Yeah, that's a
and in similar ways, right, the IF6 clones kind of compensate for that SBDS defect as well. So I think, it's a great question, Jackie. I think those natural mutations kind of prove that hypothesis in some way.
Right. Yeah.
Okay.
For sure.
Mm-hmm. Okay, any other questions from the audience? Because Jackie and I can cook up some more, but yeah. Okay, we got a question.
Hello, can you hear me?
Hi.
Yeah.
Yes. We can
Okay,
hear
good. I'm Caroline, mother of a young SDS patient from Estonia. This conversation is very advanced, and I really don't get all of this, but I have more basic question. I know there are several mutations that can be associated to the SDS, and I was wondering if a mutation, a specific one, can be associated with a specific set of features. I know that the SDS patient can have very variable in degrees or even in types of symptoms, and I was wondering if this can be associated with different mutations.
This is a really important question. Yeah, so this is right. So there are two mutations that are particularly common amongst patients with SDS in the gene SBDS that are recurrent, but there are also patients who don't have those two common variants. And there has been work looking at, large groups of patients, relatively large groups of patients with SDS, and looking if we can correlate what type of variants they have. So scientifically, we would call that the genotype of those patients, right? What variants do they have to what symptoms do they have? And we would call that the phenotype. And so we call this a genotype to phenotype connection. And can we see, okay, all of these patients with this type of variant have this symptom? And so far, there hasn't been one that stands out for patients with SDS. There's hint that patients who have mutations that we would say are where no protein is made, right, off of that gene can have a little bit of a worse presentation, right? So more symptomatic, but this isn't 100%. So we can't look at a newly diagnosed patient and say, okay, that person has these two variants, and they're going to have this list of symptoms. Unfortunately, it's not that laid out. We hope someday to be able to answer this question, but we don't have an answer to it yet. Does that make
Okay,
sense?
thank you. Yeah, thank you. It was very much understandable answer. Thank you for using
Every
plain
patient
words.
is, I think every patient is different, and their experience, that we would say, like, the experience across patients with SDS is really, really variable. And this is called, in genetics, we call this variable expressivity, meaning how they express the disorder, right, is vary from patient to patient to patient. Unlike, some disorders where every patient has exactly the same symptoms. And that's just not the case for SDS. Which is why I think it's really important for all patients with SDS to have a team, right, who can address each area of symptoms, because, right, it's not just hematological, right? It's not just gastrointestinal, right? You need all of the players to help. So, yeah.
Yeah, and
Thank
in
you.
addition to that, I think we also know from our community, just from anecdotal experience, and maybe your data shows it too, Lisa, that in some families, one child is diagnosed and then the rest of the kids are diagnosed, and some of the kids may have SDS even though they have no symptoms whatsoever. And so genetically, they have exactly the same mutation as their other sibling and a similar genetic background as their sibling, and yet one of the kids is severe and the other is not.
Yeah.
So
And
we would like to encourage all families who might be listening to this to work with their provider to try to get testing for all the kids in the family if the parents are both carriers. That would be really important to do.
And the timing is the other thing, the timing of when symptoms appear can be really different from sibling to sibling. Like, as I said, even in patients who have, they have the same pathogenic variants and they have the same genetic, all right, all their other genes are very similar as well, and they live in the same household, right? So their exposures are very similar. So this is something we'd like to really understand and don't have a good grasp on.
Lisa, do we know whether the risk of transforming to leukemia, are they worse in patients who have more severe symptoms than the pretty asymptomatic patients? Do we know any data about that?
Certainly patients who have more, low blood cell counts, right? The worse your counts are earlier in life, generally because there's more stress on the marrow in that situation, right? Versus some patients who have, go through childhood and, never need a transfusion, don't have low, neutrophil counts, right? And do generally pretty well. I think, while I don't think we have the numbers to support it just because of, the rarity of SDS, I think just given the increased stress on the bone marrow, those patients are more likely to transform. But whether that holds true in a statistically significant manner, I don't know the answer to that.
Yeah, and probably the milder patients still wouldn't get a free pass from surveillance.
Right.
Everybody really needs some sort of surveillance.
Yeah. Until we can come up with better tools, everyone needs surveillance right now.
Yeah.
Yeah.
Talking about surveillance, there are, in some countries, surveillance is now more often done on the blood versus bone marrow. As far as I know, in the U.S., they're still strongly favor the bone marrow for various reasons. It's more data, how to interpret the results, and there's more information to be gained by looking at the slides and additional information. Have you seen any trends in this regard?
Yeah, so there is, of course, a lot of discussion about this because I think we'd like to save patients from bone marrows every year if we could. I think there's pretty decent evidence that what we see in terms of somatic mutations in the blood generally reflects pretty well the bone marrow. But the other piece that you spoke about, right, the morphology, when you look at the bone marrow under the microscope on a slide, you can't get that from the blood. And I think there's a lot to be gained by looking at that, looking at it over time, right? Because some patients with bone marrow failure disorders, right, their bone marrow, even before they have any somatic mutations, looks different. And that's their normal, right, their baseline. And if you never look at that, when you have a somatic mutation and you do the bone marrow, right, you have nothing to go back.
Panic, right?
Right, like, well, okay, what did it look like when they did not have that somatic mutation, right? And so the question, I think, is like, I think it's going to be a very useful tool, obviously, to look in the blood, but could we space out those bone marrows, right? Could we extend the time in between by using, a blood test instead? I think the other piece that we miss, right, obviously when we do the peripheral blood, right, is we're not looking at the cytogenetics, right? Like whole chromosome changes in the bone marrow, and those aren't going to be picked up in the blood. And like the significance of those larger structural, abnormalities, somatically can be really important as well. And they have, because we have more data on those, we have a little bit more clue about, who's a good actor and who's a bad actor and who's I don't care, I'm just going to hang out and be here abnormality. So I think for now, I think we're still stuck with bone marrows, but I do really hope, and I think the technology will advance in time so that we can get away from doing that. I think I was speaking with somebody who was not a hematologist, and they were shocked that this was like the standard of care. And I said, yeah, this is what these patients have to go through. And it's, it's not a small thing we ask, so I think anything that we could do to get away from that would be wonderful.
Mm-hmm. Yeah. And then it gets even harder for young adults and adults with, like, even if they want to get bone marrow, which is questionable, but even if they wanted to get a bone marrow biopsy, it's logistically, insurance-wise, it gets harder also.
Very much so. Very much so.
Related to the testing, another limitation I was thinking about is that in the model you showed in that publication, the hypothesis is that if a patient has one TP53 mutation, they may be okay for a while, stable, but if they get two within the same cell, that seems to be dangerous. However, what I'm not clear about is whether our current standard testing can distinguish that, whether there is one or two mutations. And what I heard is that not formally, but like based on some, variant, the VAF, or some statistical analysis, you may be able to kind of guess, but it's like diagnostically, it's not quite an established diagnostic test whether there is one or two P53 mutations in a single cell.
Right. So certainly we can identify if two mutations, right? So when they do the sequencing, right, they take the blood and they break up all the DNA and then they sequence everything, right? So whether it came from this cell or this cell, we have no idea, right? So if a patient has two distinct, different TP53 mutations, you can identify that. But whether they're in the same cell or not can only be done by single cell technology. You can do some inference, right? If this mutation and this mutation are the exact same variant allele frequency, they're probably occurring in the same cells, right? And sometimes you can actually see a little bit of hierarchy if a patient has multiple somatic variants, right? Okay, so they've got these three variants at this variant allele frequency and these two variants at this allele frequency. These are probably two different clones, but this is 100% on statistics and numbers and isn't actually, with the single cell technologies, which are, obviously not in clinical practice yet and only in the research setting, right? They can take a single cell and figure out which mutations are, but this is not standard of care right now at all, and very expensive.
So when we hear that the patient received next generation sequencing either on blood or the bone marrow, that would be really just a bulk, like they take a part of the cells in the blood and they just do the sequencing on the whole.
Right.
On the whole
When
lot.
you send what's called like a myeloid panel, right, is what's typically called, right, that's bulk sequencing. So.
I see. And then the single cell one is currently only done on a research basis in labs.
Yep. Yes. And I don't see that coming to the clinical setting anytime soon. I mean, I think people would like it, but it is very cost prohibitive right now.
Yeah, and then you just do one single cell, right? You would have to sequence a whole bunch to have some statistic confidence.
Yeah, I mean, a typical single cell experiment has, maybe 10,000 cells. If you're lucky, you get to do 20,000 cells. And really, that is still only a snapshot of everything that's out there.
Right.
Yeah.
Mm-hmm.
More to come.
Yeah, and do you, well, I could imagine if a patient receives results that suggest that this could be a relevant question, that then certain labs would be able to do this, as on an experimental basis.
Yes. But right now, none of those things are being used for clinical management.
Yeah,
and
no decision making.
It is important to, think about what we know in the research setting versus what we feel, clinically confident to act upon. So,
yeah. I think I'm hogging the microphone, so I'm going to let the others ask questions.
Well, my only comment on that is I feel that we're still using very primitive blunt instruments on this.
I mean, it's certainly better than even when when I trained. I feel like we've come a long way since then, which isn't that long. I don't know. But yeah, I mean, there's still so much refinement to do. And I think we could get a lot better at it. And I hope that we will. I think we could help patients. I think this question of when a patient can slip over is really interesting. And I was actually at a conference last week, and I was speaking to actually a mathematical modeler, and he had this whole model of patients when they develop MDS. And okay, maybe they're in he calls this hills and valleys. And he said, well, okay, well, now you're in the valley and you're doing great. And then you climb up the hill and you're, maybe you're in the pre-leukemic setting, and what tips you over the edge into that. And had this very interesting modeling. So we're going to talk and see, and maybe there's something there that we could look at. But I think there are a lot of people smart people thinking about it. I just think we need more people doing it.
When I go back to one of the slides you were showing about the back to germline, just to how to identify whether somebody has a genetic underlying cause of a disease. And you mentioned that generally speaking in the medical community, if the chances of finding an answer is 5% or more, it's generally encouraged. But a lot of providers don't think, especially when they encounter, say, an adult or young adult patient with leukemia, they might not think that it could be something genetic. And so they might not ask for genetic testing as early in the journal as it would be beneficial to the patients. Pediatrics, maybe it's a little better. Are there any concerted efforts from within the medical community that is trying to, I'm trying to change it and encourage providers to ask?
Yeah, so this is
are there other efforts on the way to encourage more earlier
Yeah,
genetic
so I
testing.
often say this is like preaching the gospel, right? Our gospel about germline testing. So I think, amongst pediatricians, we generally think about genetic disorders, and it's not so much of a problem. I think the hardest part is the young adults, because I think there is a significant portion of young adults who are affected, and the adult providers don't necessarily think about genetics. And there are a couple of us in the, bone marrow failure and myelodysplastic syndrome world who really have been pushing and trying to, teach people and preach to people that this is really important, that young adults get tested. And that figure with the graphs that comes from a woman named Lucy Godley at the Northwestern University. And, she's an adult hematologist who feels very strongly that every, patient who comes to medical attention gets, in terms of, hematology, either bone marrow failure, myelodysplastic syndrome, acute, myeloid leukemia, that all of these patients get upfront genetic testing. So together we spend a lot of time encouraging this. And, we also, talk about this question about getting insurance to cover this is a big deal. And she made, and it's really got to me a couple, I forget, a little bit ago, she made this comment to me. She says, well, if you have a breast cancer patient in your clinic and she has a 5% chance of having a BRCA1 mutation, you send the testing and you don't even think about it. And the insurance company just rubber stamps it. And that is where we need to get to with these disorders. And we haven't gotten there yet. And I think, a young adult with marrow failure, right, has at least probably higher than 5% chance of having a genetic, cause for their marrow failures. They should get genetic testing. And why it's such a hurdle, I'm not sure. I don't know if it's because of this silo between pediatrics and adults or how this is grown up, but we're trying to change the conversation about that.
Yeah.
Well,
Yeah,
there's also a definite lack of transition care.
Oh.
And the problem is that we can't, the pediatric cohort doesn't talk to the adult cohort and vice versa. And so there's nothing for people who fall into those cracks.
It's one of the highest needs, in my opinion, is the young adult world. And transitioning kids who are diagnosed with genetic disorders as kids into the adults, and young adults who were never recognized as having a genetic disorder until they were young adults. It's a huge problem. It's a huge problem on many levels. One, you're busy, right? You're doing things like, getting, going to college, you're getting married, right? You're doing all of these things, and you don't have health insurance anymore, at least in the United States. And so it just becomes, we call it the black hole of young adulthood, and it's a major problem. So something we need to work on.
Yeah. Oh, but that example you shared with the breast cancer screening, that that it's like automatic, right? And why is that not the same for blood disorders is kind of a mystery. Mystery to me. Is it because I don't know why that would be. I know for AML, acute myeloid leukemia, the risk goes up and most patients are old. But that should even raise more alarm bells if a young person develops AML.
Right.
So hopefully we can do some advocacy from all angles and reach more people.
For sure. Definitely.
So I think we're on top of the hour. Are there any last minute pressing questions from anybody? So my last question on the list, it's a little bit more philosophical, so maybe it's a good closing question, is in the context of SDS, what keeps you up at night? Like, what do you think would be the most, a really impactful questions to ask or answer?
Yeah, that's a great question. So I would say recently it's been the insurance question. This has been plaguing me at night when I can't sleep. But I think actually the other question that got raised about the correlation between genotypes and phenotypes is something that I think we still have more work to be done on. And I think that we could help patients prognosticate if we could get better correlations between these two. And I think that would be a wonderful thing for patients. So, but
And
I do
could be,
also,
I guess, it could be also like additional genes in the background that make this
yes,
wider,
definitely.
milder or more
Right.
severe.
Right. And this 10% of patients that don't have SBDS mutations, right?
Mhm.
What else do they have, right? There has to be something that's going on.
Well, so yeah, we are really out of time, unfortunately, but thank you everybody for coming, and thank you, Lisa, or Dr. McReynolds. To be more formal, thank you so much for your time on this Sunday afternoon and for joining us. We learned a lot and really appreciate having you.
Well, thank you all for having me. It's been lovely. And if anybody has any questions, Esther has my contact info. You're welcome to reach out at any time. So thank you.
We'll definitely
Thank
do.
you.
Okay, thank you, everybody.
Have a great day.
Thank you.
Thanks. Bye.
Bye-bye.